Okay, so welcome back. Now we are going to move on to the second algorithm, which is the Rabin Karp algorithm. So this is a bit more complicated than the first one, but at the same time, it is also much more efficient than the brute force, aka the naive algorithm that we learned earlier. Okay, so we'll jump straight into the rough pseudocode of how it works first. And it's okay if you don't understand it right away. It took me quite some time too, but yeah, it's the general outline. Okay. Hey, but before that, remember how I mentioned that the Rabin Karp algorithm will actually aim to decrease the number of comparisons needed compared to the first algorithm. Okay, so I just want you to keep this in mind. Okay, so the first main step is that we'll convert P, which is our pattern, and it has length of m to a number. Number in this case will let it be small p. Okay, and secondly, we'll convert the first m characters, which is basically the first text window to a number t. Okay, and then if let's think, yeah, if p and t are equal, then we say that the pattern is found, and we exit. And lastly, if it's not the end of the text, you should note the last window we shift the text window one character right. And convert the string in it to a number t. So this is the same t as in step 2. And then we go to step 3. Else pattern isn't found, and we exit. Okay, so we just take a moment to read through this. Yeah. Okay, so let's have a simple example. Okay, so let me just start a new slide. Actually, you know what? We just stick to this slide. Let's do some space here. Okay. So let's say a simple example with t that's equals to 0, 0, 1, 0, 1. Okay, so we'll also have a new variable called d. So d is basically the number of unique characters, the maximum number of unique characters that p can have. So basically, it's the cardinality of the alphabet. And this is, in this case, is 2, because the maximum number of different unique characters that p can have is either 0 or 1. So in this case, our sigma is either, yeah, it's basically 0, 1. Yeah. Okay. So this is called sigma in this case, and we'll go through more examples later as well. Okay, so in this case over here, n is equal to 5. Because remember, m is the length of, actually I should write it over here, m equals to the length of p, which is equals to 5. And in this case, remember we want to do step 1 over here, so we convert p to a number. So how to convert this to a number is actually very straightforward. So since this is in binary, we'll just convert it to a decimal number, which is base 10. So this is 1 plus 4, so it's 5. So in this case, small p will be equals to 5. Okay, I'll just make it more obvious that this is small p. Okay, now we can move on to the next slide. Yeah, actually, let me just rewrite it over here. What p is. Then we have m equals to 5, small p equals to 5. Okay, then now let's have t. Just go through quite a long string. For example, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 0. Yeah, so I'm just using a long string to make it more robust of an example. Okay, so similar to the naive algorithm, we start with the first window over here. And remember, the length of the window is always equals to m, so it's always 5 characters. Okay, so we compare, and then instead of comparing each character as in like this against this, this against this against this, and so on and so forth, we don't need to do that. All we need to do is calculate the value of small p, which we have over here, and small t. So in this case, t is equals to, this is 2 plus 4, so it's 6. And 6 is not equals to 5, so it's a mismatch. So we move on to the next window over here. And over here, t equals to 12, because 8 plus 4, so it's another mismatch. And then we move on to the next window, so on and so forth, until we manage to find a value of small t that is equals to p. And if we do manage to find one, then that means that p isn't in t. But in this case, if you realize, by the time we come to here, this is when t equals to 5, which matches p. So this is when we stop, because t equals to p. So found p in t, which is what we want. Okay, so now you may be wondering, how exactly do we calculate the small p or the small t in the first place? Okay, so in this case, it's very straightforward because it's like converting binary to decimal. But let's say, what if it's not in binary? And this is where, in the earlier slide, when I mentioned D over here, which is basically the set of possible characters, the maximum number of possible characters that either P or T can have, and they have to be unique. It's basically the alphabet. Hey. Remember, D equals to cardinality of sigma. So let's say if it's base 2, so if it's base 2, then remember sigma is either 0 or 1. If it's base 10, then sigma equals to 0, 1, 2, so on until 9. And that means this is quite messy. D is equals to cardinality of sigma, which is equals to 10. Okay, so how do we calculate? Let's say if instead of base 2, we use base 10 for P and T. Yeah, so we'll be assuming that P and T are always the same base, because if not, then there's no point comparing them in the first place. So if it's like this, then that means D is equals to 10, because we're using base 10. So how do I calculate P? So P will be equals to 3 times 10 to the power of 4. Actually, let me just use a dot. Is a dot better? Let's see. Yeah, I think a dot. Yeah, a dot means times over here. Plus 2 times 10 to the power of 2. Ooh. plus 1 times 10 to the power of 1 plus 5. Okay, and what we are going to do now is rearrange it such that we can effectively calculate it using a for loop, and you'll see why. So what we do is we factor out the tens a bit at a time. So we're focusing on this over here, what's underlined over here, and we're factoring out 10. So factoring out 10 will give us this. Yeah, if I put this asterisk here, it's the same thing as the dot. Yeah. Plus 5. Okay, so now we're going to factor out 10 again. So now we're going to factor what's underlined over here out. I factor out 10. So this means this is 3 times 10 to the power of 2 plus 6 times 10 plus 2. And then we'll multiply this by 10. And then we fill in the rest by copying the line above it. Okay. Well, a bit the brackets are increasing, but this is expected. And then we'll factor it out all the way until we only multiply by a power of 10. So you notice over here is 4, 3, 2, and over here will be 10 to the power of 1. Yeah, so we do it until here. Once we get the 10 to the power of 1. So now we're just copying the line above it. Yeah, actually, let me just tidy this out a bit. Let's know if I did this out. Okay. Oops. Okay, sorry, we factored this out. Yeah, to get this over here. So from this you can notice a pattern is that we can generalize it to this. P is equals to P 0 times d to the power of n minus 1. You use his m is equals to 5. And it makes sense because 5 minus 1 is 4. And the maximum power here, we can see over here it is 4 over here. Yeah. Yeah, 4 here. So it's correct. And then there's the power of minus 1. Yeah, actually, let me just rewrite this. Minus 1 will be minus 2. So on until two times d plus p m minus 1. Yeah, so this is the last This is the last character. G times d to the power of 0. And this is basically equal to 1. Okay, so this form that you see over here. Okay, so let me just highlight. This part over here. Where's this test? Actually, this works. You see this part over here corresponds to this part over here. Okay, sorry, let me just make it easier. What I mean is this line over here corresponds to this line that we talked about earlier. Okay, so this basically simplifies to this straddle of brackets, where it corresponds to the last line of the example that we have. 1 C over 2 times D plus dot plus P M over 2 so let me just P minus 1. Okay, so let me do this here. Okay, so this both these stars here are equivalent to each other, and the second star is just the general formula that we want because it's easier to convert that to a for loop block. So how do we calculate it then? Okay, there's some space here at the top, right? So I'll just use it over here. So in this case, P will be equals to the first character and for J equals to 1 to M minus 1, then we'll do this P times D plus P of J, which makes sense, and we realize it's M minus 1 times. See this plus over here, that means we'll be adding M minus 1 times. And why is that so? Because, for example, let's say, remember we had 3, 3, 6, 2, 1, 5. And using this logic over here, we start off with 3. Okay. And in this case, D equals to 10. So 3 times 10. And then we'll plus 6. Yeah, in this case. And then we for the first loop. And then we do so all the way for the rest to that 3, 6, 2, 1, 5. How you can think about it is, see there are 5 characters over here, so we're going to take this value plus this value plus this value plus this value and plus this value. So there are a total of m minus 1 number of additions. Another simple way to understand it is we can see like this general formula over here. You see, given p over here, you see if you look at the numbers from we start from 0 and we end off at m minus 1. So from here we can see that there are m minus 1 number of additions. And you can still refer to the example over here. You see there's 1, 2, let me just use my mouse. You see there's 1 here, 2, 3, 4. 4 additions when n is equals to 5, which is correct. Okay, so if we look at this code over here, that means P and T can be calculated in theta of m time. Yeah, because theta of m minus 1 is equals to theta of m. Okay.